Hey folks, so in this video, I wanted to discuss this theorem from the section 2.2 packet. We had discussed a little bit about it, and we used this theorem as our algorithm, our general algorithm for finding the inverse of a matrix. But I wanted to spend a little more time just sort of exploring these ideas. So the theorem says an n by n matrix A is invertible if and only if that matrix A row reduces to the identity matrix. Now, we have discussed this previously, right? We talked about pivots and, sort of why this should be the case. So I'm not going to focus on this so much, but I want to focus on the second half, which says that the same row operations that transform that matrix A to the identity, well, they transform the identity to the inverse matrix, right? This is exactly why we have that algorithm where we set up the big augmented matrix and row reduce everything to find the inverse matrix for A. So why is this the case? Well, the key to understanding this relies in the following. So the key relies on remembering that row operations, so elementary row operations, is the same thing as multiplication by an elementary matrix. And so we spent some time in class seeing that, oh yeah, the replacement operation can be thought of as some matrix. We call it like E1, E2, whatever it was in that example. But there's a matrix that we could multiply our matrix A by, which has the same effect as doing a row operation, okay? And so in other words, right, so doing something like A becomes sort of, you could do something like 2R1 plus R2, replacing R2. So we get a new matrix, A prime, right? That's the same thing as, well, start with A, multiply by some fancy elementary matrix, and then the result I get would be that same A prime. Okay. So why do I need this observation? Well, this observation is so important because let's imagine the process of start with a matrix A, and I apply a bunch of row operations one after the other until my final result becomes the identity matrix. Well, that means I would start with A. I apply my first row operation, which means multiply on the left by, let's call it E1. And then if that's not the identity yet, then I need to apply a second row operation, which means multiply on the left again by another operation, so another matrix, E2, and so on. You continue applying row operations, and after a while, you'll apply your last row operation, and finally, after all of these multiplications, you should end up with the identity matrix. But what's really, really interesting about this is notice that if I took all of these matrices, so En minus 1, and so on up to E1, and let me just clump all those together and call them a matrix C. Then notice the equation we've just written down is some matrix C times the matrix A equals the identity. But we've seen this equation before. This is exactly the thing that says, oh, we have an inverse for A. C is the inverse matrix for A. Right? So C is A inverse, right? This is the equation, something times A becomes the identity. This is the equation we use to check for inverses. So in other words, we have just seen that all of these operations all together, all these matrices multiplied together are exactly the inverse of A. So interesting. So why do I write above that it's the same transformation? So the same elementary row operations transform the identity to A inverse. Well, it's because it's nice to think about it that way, because I can just add a little identity right in front here. And of course, that doesn't actually change anything, right? That equation that I just boxed off and this equation, well, let me finish my equation, are exactly the same, aren't they? Because adding an identity matrix doesn't change anything. But what I like is you can compare sort of this equation and this equation. And when you see them sort of side by side, you say, oh, those row operations, when I apply them to A, yeah, that becomes identity. Those same row operations, when I apply them to identity, I get A inverse. So hopefully that makes sense, and that helps you understand a little bit more about why we have this algorithm that we do in order to calculate the inverse of a matrix. Okay, if you have any questions, please let me know.